Okay, so in our previous video, we covered the R-Completeness using Dedekind's theorem, Dedekind's cards. In this video, I'm going to introduce R-Completeness from a little bit different perspective, a little bit different angle. We know that there is a well-known definition of R-Completeness theorem, which is often treated axiomatically, but I'm going to construct this from scratch. It's a little bit different from my previous video. In this video, I would like to show you that for any subset of set of real numbers, given that this subset is bounded, let's call it bounded, there exists such gamma, that this gamma is a supremum of S. That's no matter what kind of cut you take, right? There exists some list of upper bounds for this cut. And that's exactly what we proved in the previous video. And this list of upper bounds, it's either the maximum of lower class or the minimum of the upper class. So in this video, I'd like to introduce more sophisticated, but more interesting, more intriguing definition and the construction of this R-completeness. Let's construct this from scratch. So first of all, I'm going to define the subject of our analysis in a more rigorous way. First of all, we have the subset S. This subset S belongs to the power set of real numbers minus the empty set, because the S is not the empty set. It is not empty. It should not be empty. Then for any X belonging to this set S, there exists such M, like for any S, there exists such M, right? That this X is smaller than or equal to this M. That means it is bounded. That's just a formal definition of being bounded. By our construction, we have to construct and prove that there is such gamma that also belongs to a set of real numbers, which serves as a supremum of the non-empty bounded set S. So to begin with, I would like to get started with the definition of real numbers. By definition, the set of real numbers, as we defined that in our previous episode, actually, that was the set of alpha such that alpha defines the cod, which is the cod, over the set of rational numbers. This is by construction. This is our construction. And then we define the set S. Let's call it the proper subset of set of real numbers. Again, this is by definition. And therefore, for any S, no, let's call it this way. For any alpha from the subset S, alpha defines the following cod: A alpha and A prime alpha, right? So again, this is over a set of rational numbers, i.e. the union of these two is a set of rational numbers and their intersection is the empty set. Cool. Now I'm going to let's define two sets or subsets. The first one is the C, which is the union of A alpha. Alpha belongs to S. And the second one is C prime. The C prime is just the difference between the set of rational numbers and the C. Now that we have defined this, since our S is not empty set by definition, therefore there exists at least one alpha which belongs to a set S, such that alpha is apparently the real number. Therefore, A alpha is not the empty set. Consequently, the union of these sets alpha S is not the empty set as well, which is equivalent to C is not empty. Now let's prove the boundness of C. For any alpha that belongs to C, alpha belongs to some A alpha. And therefore, by our definition, this alpha is lower than alpha prime, which belongs to A alpha, A prime alpha, by definition of Dedekind's cut. Therefore, the C itself is bounded, because for any value from C, we can find such a value that is greater than that, and then it's kind of bounded. And since it is bounded and it is non-empty, that actually means the same applies for C prime. But before getting to this, I would like to introduce the valid cut U prime, which belongs to a set of real numbers. And such valid cut exists because C is bounded. I'm going to define this cut the following way. For any alpha that belongs to C, this alpha is lower than U. And this is basically the upper bound. U is the upper bound. Therefore, since it is smaller than U, by definition of the Dedekind's cut, A alpha would be the subset of U. But since that applies to any alpha from C, we can therefore imply that union of these sets would be also the subset of U, which is equivalent to C is the subset of U, which means, again, by definition, Dedekind's cut that C prime is the complement of C, is the superset of U prime. Given the fact that U prime is not the empty set by definition of Dedekind's cut, therefore, the C prime is not the empty set as well. Consequently, we have defined C and we have defined C prime. Both are not empty sets, both are valid. Now, This moves us to the step number 3. Here, I'm going to define two elements, the C and C prime. Let C belongs to C, and C prime belongs to C prime, the lower and upper classes. Now, here's where it gets interesting, because from the C that belongs to C upper, the lower class, therefore, there exists such alpha 0, which belongs to S, that C belongs to this lower class of alpha 0. And if C prime belongs to C prime, therefore C prime does not belong to C, which means that C prime does not belong to alpha 0 lower cut, which means it can only belong by the definition of Dedekind's cut to A prime alpha 0. From this it follows that C is by definition of Dedekind's cut smaller than C prime. Therefore, for any C which belongs to C and C prime that belongs to C prime, that entails that C is smaller than strictly smaller than C prime, which implies that there exists some gamma which is the valid cut of C, C prime, because we have already established that these are not empty sets, and for any value from the lower class, from any value from the upper class, the value from lower class is always smaller than the value from upper class. That defines that as the valid cut. Cool. Now that we have defined the valid cut C, C prime, all we have to do here, all that is left to do here is just establish the bound, right? So we already know that there's some sort of cut here, which is called gamma, but we don't know whether this cut is the bound or not, and we don't know if this is the smallest bound or not. So first of all, for any alpha that belongs to S, we know that A alpha is the subset of C, and therefore alpha is the smaller than equal to gamma. Well, that's pretty much obvious. It follows from the definition of a Dedekind's cut again. And therefore, the gamma would be the bound, the upper bound of our set S. Now, let's denote V, which is the V and V prime, as any upper bound of S. Therefore, for any alpha that belongs to S, alpha is smaller than or equal to V by the definition of that, which is equivalent logically to saying that A alpha is the subset of V, which means that the union of this is the subset of V, which is equivalent to C is the subset of V, the proper subset of V, which means by definition of the cut that gamma is smaller than or equal to V. That's the gamma which defines this cut C, C prime is the smallest of all possible upper bounds, which means that our gamma is essentially the supremum. So this is the whole proof behind this problem. It is pretty simple. It is more sophisticated, more rigorous than the previous one, and it formalizes the definition of R-completeness over the bounded set, over the bounded subset